Up next, we have Building Advanced Protocols with BitVMX from the BitVMX Principal Engineer, Martin. Please give a very warm welcome. Thank you.
Yep. Okay. Hey, hello everyone. Thank you for having me here. Well, today we are gonna present building advanced Bitcoin protocols with BitVMX. I mean, the idea is that we are going to talk about BitVMX as a platform for creating other applications on top of it, and we are going to explore the components that helps on these different type of problems that we will need to solve for creating these type of applications. Then we will move into some of the innovations that we did. Yep, let's start. So, what is BitVMX? Well, first of all, I think obviously we saw the previous presentation from Robin. 2 years ago, he presented BitVM. That in that way opened the door for a new type of smart contract on Bitcoin using disputable computation. This actually was possible even without changing consensus on Bitcoin, what wasn't possible before. Basically, the idea, I mean, the BitVMX is a little different on the other version of BitVM. It's not like BitVM 1, 2, or 3. It's a completely different implementation that is based on a RISC-V emulator. The idea is that instead of the verification being executed directly on chain with a Groth16 verifier, we are running a program that can be verify any type of verifications that we decide. In particular, we are using Groth16, but this is just because of it is in a way reduce the size of the inputs of the programs that we want to verify, and that's the reason chosen. But also one of the possibilities that provides having a RISC-V processor in a way that we can, in example, verify a counterproof given by another party, right? I mean, the prover could provide a proof, and the verifier can provide a counterproof, and those will compare, and that's what part of the flexibility that gives the idea of having a CPU for running this. In particular, this has been shown too, but the idea is that always these kind of protocols have a happy path where if both parties agree on off-chain, they could basically sign a new transaction that will move the funds from the locked funds in the previous locked in the UTXO. And if in case of dispute, in case there are no agreement there, there will be a dispute on chain, but only on those cases. Just one other thing, that because it was a comparison between regarding the sizes of the cost of running a BitVM2 that was about 6 megabytes, or in worst case, BitVMX as it is today is around 600 kilobytes. I mean, it's much smaller, the cost on chain. It's at the expense of having another set of rounds of challenges of transactions, but the cost today is already much closer of what would be a garblet circuit version. So I want to talk about two applications that we already built using BitVMX. We have designed two bridges. One for Rootstock, like it's a bridge between Bitcoin and the Rootstock layer 2 blockchain. It's an improvement on the assumption of security. Their previous bridge has a committee of around 11 operators that you need to have more than half of those operators to be honest in order to the bridge to be secure. This implementation using BitVMX reduced that to 1 of n honest assumption, and also allows you to increase the number of operators, because you don't have like a problem where a lot of operators can gather together and collide together to reduce. See, actually, increasing the number of operators increase the security. And on the other hand, we have the Cardinal protocol. That's another application that we build using BitVMX. The idea is that we can, if you have an ordinal or an FT on Bitcoin, you will be able to log this on OTXO on Bitcoin, and this will enable you to trade this NFT on Cardano network, right? I mean, you can, for example, put it as part of a loan on Cardano, and then get back into Bitcoin later after trading or whatever you want to do, or DeFi application that you need to run on there. Also, it's a one of n honest assumption, and something interesting is this using the transfer of ownership protocol. The idea of this protocol is that there is no time in the process of all the breaching that the ordinal gets in the hands of the operator. So there is no risk that the operator will take the ordinal. The cost of this can be varied. So it also reduces the need of having a collateral as part of the operators. So these are some design decisions that we took in order to, when we start working on the implementation of BitVMX, we wanted to have something pragmatic. The idea is to have to be able to release real life and production grade code. We didn't want to have like a POC or a theoretical implementation. We have something that other parties can use and build on top. So it needs to be robust in that sense. We wanted to be protocol agnostic. The idea is that actually what happened, that we are not tied to any of the breach particular details for implementing this. So again, I mean, we were able to implement 2 solutions on top, and we are in the process, and we could implement other solutions. We are not tied to any of these. Modular, because we wanted to reuse the components that we write, we were able to switch them, and in general, the solution is presented as modular for us to use it. Fault tolerant, we have to create this and say in a way, as Robin mentioned, I mean, all the breach you need to have like a whole graph of transactions that control the logic of the smart contract that you build, and in a way, if you lose any of this information that you generate on setup, you probably won't be able to regenerate that. So we need to have very robust infrastructure to support that and don't lose anything and continue. Adversarial robust. I mean, the idea here is we are gonna be doing a setup. I mean, during the setup phase of the protocols or these applications that we build, you usually have to collaborate with other operators in order to generate the smart contracts. The thing is, these communications needs to be secure, because actually the same operator that you are trusting in that time for the setup could be adversarials that are trying to attack you. So the security measures needs to be in place for this to work well. Scalable. We are supposing to be, I mean, one instance of BitVMX needs to be able to handle up to thousands maybe of locked funds in the same instance of BitVMX. BitVMX will control one instance of BitVMX needs to be able to control a lot of these of TXOs. And not for that less important is we decided to use standard transactions. We didn't want to be in the situation of needed to use one specific mining pool for being able to send our transactions. That in a way makes the problem of censorship bigger, right? I mean, if you only depend on one particular pool that will send your non-standard transactions. So all the protocol is designed with standard transactions. So for the building blocks of BitVMX, we have we needed to have something to run this verification execution of chain of the information of the parties. We need then something to have the validation on chain. We need something to help on the proof generation. We're using RISC0 for generate the proof, but the thing is the time to generate the proof usually takes may take hours. So how exactly this connects in the architecture to generate the proof, get the information back, and put this as part of the input of the program is important. We need to generate a graph of transactions that needs to be agreed on setup. We need to have persistent storage. We need to have transaction signing, and for the transaction signing, it's not only the signing of the transaction, the regular Bitcoin transactions, but we also will need to use WinTernet's one-time signatures. That's the way to encode the information into these smart contracts. As you might know, Bitcoin script doesn't have reflection on other transactions. You cannot go and get the input that other party put in one transaction, take it and use it in the next transaction. So for solving that problem, we are using WinTernet's one-time signature is the way to use those kind of connectors that Roy mentioned. And so we need to have something that handles this type of signatures too. Then we have obviously something to connect with, handles the Bitcoin connection for monitoring and for dispatching transactions. We need to have connection between subsystems and connection between operators. On top of that, obviously, there is an orchestration of all of this. Well, in this graph, if you can see, we have in the yellow boxes, we have like the external parts that of the system, Bitcoin, the Bitcoin core, the Bitcoin network. There is zero instances that will generate the zero knowledge proof. We have the protocol layers that will be built on top of BitVMX, and on the top right. Right there, in light green, is the rest of the operators. In the center, we have like the whole BitVMX instance controlled in the center by the BitVMX client, and what is around is the rest of the components for communication, for key manager. We will see those on detail. So one of the main components is the BitVMX CPU. Basically, this component serves three main purposes, being like maybe the first is the execution of chain of the input provided by the prover. Then we need to have something, as BitVMX works, at some point we will need to try to find, in case of challenge, we need to try to find like one step that we agree, both parties agree, and one step that there is a disagreement. And the idea here is that the only thing that we need to be executed on Bitcoin will be one of the opcodes of RISC-V, and for that we need to have all the RISC-V opcodes mapped into Bitcoin script. That's something that also this module has implemented. And on top of that, also this module is responsible for handling the logic on all of this dispute, trying to find the dispute step and to choose in the set of possible challenges that are maybe required to challenge an operator in case it's malicious, and also help the prover to, if it's the honest one, to respond in the right way to actually win the challenge if it's badly challenged. Okay, protocol builder. So, as we mentioned before, all of these protocols or applications that we build up are mainly based on a big graph of pre-signed transactions. And building this transaction is not easy. And what this module does is, in a way, abstracts the part of creating the nuances of the Bitcoin transactions itself and allows you to design the connections. I mean, it's more focused on the logic that you want to achieve with the protocol itself. So this is the main purpose of the of the protocol builder. It allows you to, as I mentioned, do this to create different types of transaction. It stores metadata that will be used in order to sign those Winternet transactions or decode those Winternet signatures from the transactions seen on chain. It helps in the creation of chain page for parent transactions that are used for actually ensure that transactions are sent on chain. It also helps on dust and transaction fee calculation. As I mentioned, this is our big graph, may have different branches, or it becomes very difficult to do by hand the computation of how much dust and the transaction fee you need for this. And also it has some interesting debugging capabilities to show and to visualize the graph itself produced by the protocol builder. For storage, we are using RocksDB as backend. It's a key value database. We choose to this because it's very performant, supports transacted operation. That is key for the part of being fault tolerant. It's simple and in a way also agnostic and gives you the flexibility for the other applications that are built on top to store information without requiring to have like a more structured database for doing that. On top of that, we have an encryption layer for storing keys or partial signatures or important information that cannot be disclosed. We have a key manager. It handles the key generation and handling of these keys. We are not only supporting ACDCA, Schnorr that are obviously required for signing the transaction, but we are handling all the Music2 protocol for aggregated signatures. This protocol allows you to have like one signature more efficient that have like another type of multi-sigs on Bitcoin, but for doing this you need a kind of round protocol where the party sends its public key, then it sends the nonces, and then you may need to share partial signatures. So this is handled in part by the key manager. Then it's of course, as I mentioned, the Winternet one-time signatures, and finally RSA, because we need, as I mentioned, to have secure communication between operators and between subsystems. So we have a way to sign this using TLS. So for the Bitcoin components, we have an indexer. It's actually 3 modules. Are the indexer to keep track of the state of the blockchain. Have the indexed information that helps to our modules to work fast and more efficiently. We have a monitor. Basically, the monitor, once we build this huge graph of transaction, is responsible of tracking the transactions on chain. What this means is, for example, we need to be able to react in the time that we saw a transaction from an operator claiming that he owns a specific UTXO. So it's important to have a module that is responsible for tracking tracking this and notifying this information in case of it's happening to the upper layers. In some cases, we need to track external transaction because, for example, when some external user wants to put money on the bridge or needs to send something to on a specific UTXO, they might be informing by other means from transactions. So we need to be able to track this transaction and see if they are present on the blockchain. And of course, we need to be able to confirm the state of our own dispatched transactions. Also, we have a coordinator module that is the one that dispatches the transaction requested by BitVMX and may send transactions of the application that's built on top. This also ensures that the transactions are sent, and if there is always there are a jailbreak for parent transaction to make sure that the transactions are sent, because we cannot predict the fee of the transaction beforehand. So this module ensures that the jailbreak for parents and replaced by fee transactions are put on chain and handles the increasing fees if necessary for ensuring dispatch. For communication, we have created a message broker between to send message between modules and also between operators. We are using it's based on TarPC. This repository from Google that handles remote procedure calls. And the idea is that we have this communication encrypted with TLS. We also have we are handling PNet certificates for the client and the server, because we also have allow list and routing conditions, because in a sense we need to make sure that the users that the bridge informs, that the operators that inform that are able to connect or to set up something, are the only ones that can be connected, and not others, because it's a security risk on have open ports and stuff. We use this module, as I mentioned, to connect not only with the rest of the operator, but to connect subsystem being the other application built on top, or the RISC zero generation module, or the CPU itself. Okay, the RISC zero proof generation helper. Basically, the idea here is, as I mentioned, the generation time of the zero knowledge proof usually may take hours, and may take hours running on a specific hardware. So having a specialized hardware on Amazon instance is something that you may require on these types of setups. So the idea is that this tool will, in the moment that there is the necessity for generating some proof, will start the instance, will generate the proof, and then will turn it off again, because the price of having those kind of instances running all the time doesn't make sense. Okay, and the last component is the BitVMX client itself. It handles the request and made by the operators protocols made on top. The idea is that it has an API to connect with the other applications. It helps on the setup of these protocols, or orchestrate the rest of the modules to communicate itself, to be able to exchange the keys, the signatures, pre-generate the graph needed for this kind of disputes, and then of course is able to track this transaction and help on automatically resolve the dispute of the dispute channel part of the transactions. Well, so for garblet circuits, BitVMX will be supporting it. It will be integrated in future versions. The idea of having BitVMX made in a modular way is that we were able to switch components easily. Probably the only component that we may need to change is the CPU, and probably modify a little bit the dispute channel to work with garblet circuit. But the rest of the components will remain the same, and their integration with the applications built on top probably too. So what we want to enforce or try to show here is that BitVMX is like a platform that allows you to build on top and kind of forget what's the solution that you have there for as an engine to solve this kind of dispute. We are open sourcing. We started open sourcing all the protocols. The protocols. No, the repositories. We started some time ago. We will end up open sourcing the rest on the next month. We are also creating an SDK. This SDK will help and simplify the ability to create other applications on top. We'll be presenting this probably soon, and also with some front-end example to help you create some application on top. So now the idea is to present some cool stuff, some cool ideas that we think that we found during the process of implementing BitVMX. Yeah, let's see some of those. First, there is we created something that we call claim gates. There is a problem that exists when you have a big graph of transaction with different endpoints that will end up with the same result. I mean, for example, you can have maybe several timeouts transactions that needs to be executed, and these claim gates, the idea is that will help you to reduce the number of transactions needed to connect this action, the action that we need to execute for these different ends, right? So avoids replicating a lot of information. Also reduce in case of depending on the time logs of these transactions. Usually you have several time logs depending on the stage, and the thing is, this protocol will, or subprotocol, or will allow you to just use the minimum of those time logs. Okay, so let me show you a little bit how it looks. I hope it's readable. I don't know, maybe. So on the top, we have a protocol, a sample protocol that could be a dispute between Alice and Bob. The idea is like usually you have turn-based transactions. So, for example, Alice is on greens trying to send a transaction, then is a reply from Bob. But if Bob doesn't reply on time, then there is a chance of Alice to penalize Bob for not putting this input on chain. And these kind of things happen all the time in a lot of transactions. And the thing is, usually what you want to connect is this for a specific result or a specific action, or actually taking the funds. But this makes, if you need to tie this every of these cases of success, you end up having replicating a lot of transactions. So for that, in the bottom here we have the claim gate. The idea is at any time Alice could make a claim. The claim in this case is I won, right? And if you see there is a yellow box from Bob that says Bob stops Alice. So the idea is, if Alice actually didn't won, there is a pre-signed transaction that would allow Bob to penalize Alice immediately, right? That's the idea. So how Alice can actually put this claim on chain? Well, for that, first it needs to consume the enabler that will allow Bob to stop her. So the simplification is that you only need to consume that simple be out from the transaction in each of the cases that actually Alice won, and then you have a claim gate to actually perform the execution of the action. Yeah, after in this part, if after time lock Bob cannot claim that that Alice didn't want, Alice can put the Alice won success transaction. We have some enabler that will actually allow her to execute the action that you want. In this case, maybe taking the funds, or maybe other claim gates that can be chained together. We have this is another thing. This is a library that we have created the last year. Basically, it's a library that helps creating Bitcoin scripts. We have used this to implement the optimized version of Blake 3 and SHA-256. These libraries, these algorithms are the ones that are being used currently by BitVM2. We use it too for creating all the RISC-V opcodes and to create the dispute channel challenges. What are the key features of the library? The idea is that when you want to write Bitcoin scripts, in the moment that you start moving elements from the stack, it starts becoming very difficult. It's complex to manipulate the elements because they start moving and you need to track where those elements are, and it's difficult. So what this stack tracker permits is to define some kind of variable or struct that will point to a group of these elements and will allow you to operate with them. In a sense, you can move them together, you can split it, you can access some part of it independently. It's really, really helpful. And also, we have a debugger. I was inspired by Johan Halset. I think I saw him here before. He presented something similar in Austin last year. Basically, having the ability to debug big Bitcoin scripts is like a key for doing this. There are a couple of IDs on chain, on the web, but they are not good enough when you start doing something very big. And we have an optimizer that solves like small cases of that needs to be optimized from the script, but at the end you end up gaining maybe 1% extra of size because it removes some silly things like from old stack to alt stack, things that end up being duplicated unnecessarily. So it removes that. This is how the debugger looks like. Not sure if it's more or less clear. The idea is that you can see how the elements moves on the stack to the alt stack and the operation that you are executing. It is open source. You can grab it from there. There is also an article about the optimization of scripts that shows a little bit more about the scripts itself and how it works. Okay, and one more. We have we encounter a problem with the minimum relay fee of the transactions. Basically, the problem was that as we put like really big inputs of the programs into transactions in part of the transaction graph, and as we mentioned, these transactions need to be pre-signed. This also means that the cost for the transactions needs to be paid upfront. Needs to be locked in the UTXO before actually, when in the moment of setup. And doing this force you to, when we discovered this, we noticed that if the witness of the transaction were very big, we end up having a lot of money pre-allocated on the setup, and that was not efficient and was starting to be very costly. So the solution was to move the inputs into the chain pair for parent transactions. The idea here is that we were already using JPair for parent transactions because you can, in a way, you're impossible to forecast the transaction fee in advance. So we need to send the transactions, being able to pay for these transactions with an independent wallet, and having that enable us to actually move the conditions that were checked on part of the flow of the transactions into the spend of this the chain pair for parent transaction. This reduced a lot the cost of the protocol, making it more capital efficient. We need to add some extra transaction log time transactions to penalize for not putting this input on chain also, but then at the end it's also more efficient.